Okay, now we're going to talk on ATP, adenosine triphosphate. Adenosine triphosphate. I set this within the DNA RNA section, even though it has absolutely nothing to do with genetics. You see, in chemistry, one chemical can act in many different roles, and they don't have to have anything to do with one another. Adenosine triphosphate has the same ingredients, I guess you could say, as DNA and RNA. It has a nitrogenous base, adenosine, and it has 3 phosphates, adenosine triphosphate, and it's got a sugar. And it's got a sugar, as you can see here, which is ribose. So it has the same ingredients, but however, it doesn't act anywhere in the same manner. ATP is our energy battery. So here's the situation. When we eat food, we don't work directly off the food. What food does is gets metabolized. The energy is released. It's an exergonic process. Keep that word exergonic. And what it does is charge up our energy battery, ATP. So we work off our battery. We do not work directly off the food. Okay, as you can see, as I mentioned. The energy of ATP is located in its chemical bonds. Chemical bonds possess energy. Once the bond is broken using an enzyme, remember, we don't want to break the bond until we need it. We don't want to break the bond. See, other words, if energy in a battery, let's say a ever-ready battery, just spontaneously discharged, how can we use it? It would already be gone. So we have to have it in such a way that we want to discharge the battery when we want to. So an enzyme would come in and break the bond and release the energy when we need it. It's an exergonic reaction. Here's ATP. Adenine hooked to ribose, hooked to 3 phosphates. These bonds have energy. This phosphate and that phosphate, because of these O's, want to repel. See, those O's, remember, like charges want to repel. But the bond is stronger than the repulsion. But if you could twist this bond a little bit, and that's what the enzyme does, ATPase enzyme. If you could twist this, torse it a little bit, this phosphate would come flying off like a bullet. Because the energy is there. The energy is there. So when you look at it, here would be it again. See, those bonds have strength in them. You just need to torse it a little bit. Adenosine triphosphate. Okay. Here's another one. The ejected acts like a bullet hitting the endergonic atom. So the way I am placing it this. Okay. You have a gun, let's say, and you have 2 blocks sitting on a table. You'd like one block to join with the other block, but they can't do it because they don't have enough energy. So you take the gun, you shoot the bullet. Now the bullet has energy. The bullet then hits the first block. At the time it hits the first block, in that instantaneous moment in time, which is very brief, that would be an intermediary step, because now the bullet will impart the energy to the block. The bullet then will fall away because the energy now is given to the block, and the block now will push into the other block and join them. So basically what happens is when you twist the bond, you eject the phosphate. It acts like a bullet. And then the bullet goes and drives some endergonic reaction. Endergonic needs energy, and that's how the whole thing goes. So this is what you're looking at. You come in, you break it off, and it ejects. There's about 7.3 kilocalories per mole of ATP. About, remember a mole, 6.02 times 10 to the 23rd, about 7.3 kilocalories. Okay, here again, it's looking at it. All right, now we come to this, which you've seen before. All right, so ATP here, ATP has energy. So it's exergonic. There's energy. But you still have this hump to overcome. That's what the enzymes got to do. Because even though it's exergonic, spontaneous, you can't drop that heel, we've explained this before, without overcoming that hump. So what's going to take that hump down? ATPase. Enzymes lower the energy of activation. So then, once that happens, it goes to ADP. See, this is tri, that's di. It lost a phosphate. It lost a phosphate. The phosphate then went out and energized something. So here's kind of something, a little schematic I tried to do if you can understand it. Here's food. Food has energy in it. Food is the way we get our energy. Food's exergonic. But in order to overcome the hump, we must digest the food. We must move the energy. Now, what's doing it? Our digestive enzymes. Our digestive enzymes are coming in and metabolizing the food to release the energy. So then the food loses its energy. All right. Now, what we need to do is to harness that energy. Now, here comes something I want to state. Anytime energy is released and there's nothing at that very, very moment to harness it, all of it will go away as heat. Remember, heat is the way the universe likes. Randomized entropy. So when the food is released, an enzyme has to hook it up with the ATP. Now it's really hooking it up with the ADP, because what the job is to take and push that bullet back into the gun. To push that bullet back in the gun. To take ADP and make it go back to ATP. That's an endergonic process. So I go back again, try to understand what I'm saying. So here's the food. Enzymes would metabolize the food and release energy. Once that occurs, then that energy would recharge ATP. Recharge ATP. And then we would use the ATP to drive some reaction that we needed. Maybe to build a muscle or something. So food releases energy. Enzymes help it. The energy released from the food pushes the phosphate back to ADP to make ATP. And then you use the ATP as our energy battery to do various things in the body. Run, dance, whatever. So here goes again. Food to ATP to drive an endergonic reaction. Food gives off energy to restore our energy battery, ATP from ADP. ATP donates energy to an endergonic reaction. The endergonic reaction now has the energy and can proceed. Okay. I go to the last, what I want to mention, and this is another time that the same ingredients are used as in DNA, RNA, and now ATP. This is what we call cyclic 3,5-AMP. Adenosine again, adenine, ribose, but this phosphate is cycling around. Now, I'm not going to say much on this, but I will say this right here is going to act as something we'll call a secondary messenger. I'll bring it back up. So see, you keep referring back throughout AP1 and AP2 into the biochemistry aspect of my, and you can see then where it fits in. So this is kind of like a reference. The last statement I'm going to make is, up to now, we've kept everything independent. Carbohydrates separate from lipids. Lipids separate from proteins. But what you're going to see throughout the course, and even starting in chapter 3, is that many of our molecules are combination. So like a glycolipid is one molecule, part carb, part lipid. part carb, part lipid. A glycoprotein, part carb, part protein. A lipoprotein, part protein, part lipid. So I kept them independent, but you're going to see we're going to be using combinations a little bit later. This actually ends the Chapter 2 chemistry. I've done organic and inorganic. Thank you.